How can we tell whether a given vector belongs to the span of a set of vectors, and how can we tell whether a set of vectors is linearly independent? This quiz illustrates examples of both of those questions. First of all, in this quiz, you're given these four vectors. They belong to four-dimensional space, v1, v2, v3, and also a vector I call b. And the first question is, does the vector b belong to the span of v1, v2, and v3? Is b an element of that span? Remember that by definition, the span of a set of vectors consists of all possible linear combinations of those vectors, where the weights are chosen from among all possible real numbers. So really, the question of whether b is an element of this set is the question, is b a linear combination of v1, v2, and v3? Is this vector a linear combination of those three vectors? And the way to answer that question is to transform the linear combination that's happening in this definition into a matrix vector product, because then that allows us to use the tools of linear algebra to know something about an equation with that matrix vector product in it. So the key is to re-envision this linear combination C1v1 plus C2v2 plus C3v3 as instead being the matrix product of the matrix having v1, v2, and v3 as its columns, and having an unknown vector x here whose components are c1, c2, and c3 as the factor on the right. In other words, this linear combination is equal to the product of this matrix times the vector c1, c2, c3, where this vector now is an arbitrary vector chosen from among three space. So framed in that way, the question of whether b is an element of this set becomes the question, is b equal to that matrix times some unknown vector x? In other words, does that system of equations, b equals this matrix times x, does that system have a solution? If it has a solution, then its solution tells me exactly the weights c1, c2, and c3 for which b is a linear combination of v1, v2, and v3. So as with everywhere in linear algebra, the key is taking the definition and transforming the definition into something which is what I call algebraically actionable, translated into an equation that we can now use the tools that we understand to know something about. So really this becomes a question of consistency. Is this equation consistent? And so to find that out, we set up an augmented system, the way that we would to try to find the solution of any linear equation. And then we perform the elementary row operations necessary. I'm going to spare the details in this video, but you can feel free to do those details on your own. A reduced row echelon form for this matrix looks like this. 1, 0, minus 2, and then 7. 0, 1, 1, and then 2. And then both the third and fourth rows all vanish completely, both in the coefficient matrix and also in the vector on the right-hand side. That's really good news, because these third and fourth rows correspond to the true equations 0 equals 0, and therefore there's nothing in this reduced row echelon form that indicates that the system is inconsistent. Therefore, the system has a solution. And because this equation is consistent, we conclude that yes, there is at least one vector x for which this matrix times x is equal to b. And therefore, b is equal to a linear combination of v1, v2, and v3. So by definition, b is an element of the span of v1, v2, and v3. More explicitly, the question then goes on to ask, if it's true that b is an element of this span, then what is an example of a specific linear combination of v1, v2, and v3 that gives us b? And the good news is, we've done all of the hard work necessary to discover such a possibility. All we have to do is finish solving this equation by describing its solution set. Let's do so in parametric form. To do so, we notice that the first two columns in the coefficient matrix have pivots, but the third column does not, and therefore corresponds to a free parameter. And so the third variable, which I'm going to call x3, that third variable is equal to a free parameter that I'm going to name t. So I get to choose a value for x3, and the value that I choose for x3 will then determine the values for x1 and x2. To see how, just rearrange this first and second equations. The second equation can be rearranged to solve for x2 and get x2 is equal to 2 minus 1t. And the first equation can be rearranged to solve for x1 and get x1 is equal to 7 plus 2t. Now that we have a description of the solution space, this describes every single possible combination of v1, v2, and v3, which form the vector b. If I want one specific example, I now have the freedom to choose one specific value for t. Let's suppose I pick t equals 3 just out of a hat. If I pick 3 for t, that determines the value of x3, the third component in this vector, but then it also determines the values of x1 and x2. x1 is 7 plus 2 times 3, x2 is 2 minus 3, and x3 is 3. And so the vector x that I get when I choose t equals 3 is the vector 13, negative 1, 3. So what that's telling me is that b is equal to my matrix times the vector 13 minus 1, 3. But remember, the whole point of setting this matrix vector equation up in the first place was that it tells me about a linear combination of those columns. And so reinterpreting this matrix vector product as the linear combination 13 of the first column plus negative 1 of the second column plus 3 of the third column gives me an explicit linear combination that takes v1, v2, and v3 and combines them into exactly the vector b. Of course, this is one of only infinitely many possibilities that I could have chosen because I got a free choice of my t here, but this is one explicit example that works. So that's how we can tell that a given vector belongs to, or doesn't, the span of another given set of vectors. That's really a question about whether or not this matrix vector equation is consistent. And in this example, we said that the answer was yes. Next, we want to know something a little bit more. We want to know whether this set of three vectors that we just studied, v1, v2, and v3, forms a linearly independent set. And ideally, let's try to do so without reinventing the wheel, given that we've done a bunch of work with these vectors in the first question. So first of all, what is linear independence? Remember that the definition of linear independence says that v1, v2, and v3 are linearly independent, exactly in the case where any linear combination of those vectors which forms the zero vector must necessarily have been the trivial linear combination. In other words, the only way to make a linear combination of these vectors equal to the zero vector is to choose the linear combination whose weights are all equal to 0. And as with the last example, the key to making this algebraically actionable is to transform this linear combination equation into a matrix vector equation in the same way that we did before, by envisioning this left-hand side as the matrix product, of the matrix whose columns are v1, v2, and v3, times the vector whose entries are the weights, c1, c2, and c3. Doing that transforms this homogeneous vector equation into a homogeneous matrix vector equation. Matrix A times unknown vector x is equal to the zero vector. So again, we're going to be answering this question by solving a linear equation. The only difference now is that the right-hand side of this linear equation, which is going to tell me something about linear independence, is the zero vector, rather than some other b vector like it was in the first problem. Well, if we've framed the premise of this implication here in terms of a matrix and a vector, we should also frame the conclusion. If all three of my weights are equal to 0, that must then mean that the only solution of this matrix vector equation is the zero vector. So another way to understand what this is, linear independence, is that v1, v2, and v3 are linearly independent if, when I solve this matrix vector equation called the homogeneous equation, then the only solution, the unique solution to it, is the zero vector. If there exists any other solution besides the zero vector to this homogeneous equation, then the set of vectors is not linearly independent. So clearly, now we have an algebraically actionable problem, and we should just try to solve the matrix vector equation. This matrix times x is equal to the zero vector. Fortunately for us, when we put the zero vector into the augmented matrix, we've already done all the elementary row operations that we need to do to row reduce the coefficient matrix completely in the first problem. So if I do those same steps again, I end up with the same row echelon coefficient matrix on the left side, but on the right side of my augment bar, now I still have just the zero vector. Because if we start with the zero vector in any column of a matrix, it's going to remain the zero vector throughout all elementary row operations. So we know for sure the reduced row echelon form is going to look like this. So what do we gain? Well, again, the third and the fourth rows are both the true equation, 0 equals 0, and so this is still a consistent equation. But that should have been obvious, because the homogeneous equation for any matrix is always consistent, because the zero vector will always be a solution of this equation, regardless. So it's not the consistency that we're interested in now. What we're interested in instead is that solution unique? Or is there more than one solution to this equation? And to understand that, we go again to looking at the basic variables and the free variables. And in this matrix, there is one column right here that doesn't have a pivot, and therefore the corresponding variable is a free variable. And because there is a free variable, that means that we get to choose any value we want to for that free parameter, and it will determine the values of the other variables. In particular, that means that our solution is not unique, because I could choose a value for that variable that's different from the one that you choose, but each of us is going to be able to build a different solution that's going to work to solve this system. So the solution is not unique, which means right away we know that this linear independence criterion is not going to be satisfied. Just to be absolutely explicit about it, let's again write the parametric solution completely. x3 is my free parameter. I'm going to call it t once again. Rearranging the first and second rows into the equation form and solving them for t, I find x1 is equal to 2t, x2 is equal to minus 1 times t. And then again, if I want a specific solution, I should just choose a value for t and figure out what happens. This time, I do have a slight criterion though, because if I chose t equal to 0, if x3 were 0, then so would be x2 and x1. It would wipe out all of my solutions here. All of my weights would be 0. And that's not actually the solution that we're most interested in when it comes to linear independence. So I should try choosing a value for this parameter which is not 0. Let's say I choose t equals 1. If I choose t equals 1, then x1 is 2, x2 is negative 1, x3 is positive 1. And what that's telling me, again, is that the homogeneous equation for this matrix has as one of its solutions the vector 2 minus 1, 1. But again, reframing matrix vector product as linear combination, what is that telling me? That's telling me that 2 of the first column plus negative 1 of the second column plus 1 of the third column is equal to the 0 vector. But those columns are our v vectors. So what we're really saying here is 2 times v1 plus negative 1 times v2 plus 1 times v3 is equal to the 0 vector. And so the premise of the linear independence definition is satisfied, that there exists a linear combination of these vectors which is equal to 0. However, the conclusion is not satisfied, because it's not true that my vector was the 0 vector. And therefore, since a non-trivial solution existed, a non-zero vector for which ax was equal to 0, we must conclude that this set of vectors was not linearly independent. To finish, the fact that these three vectors are not linearly independent also implies that one of them can be written as a linear combination of the others. And this equation that we just discovered, that relates v1, v2, and v3 to the 0 vector by linear combination, can actually show us how. For example, if I take this minus v2 from the left side and I add it to both sides, add v2 to both sides, I find out that v2 can be expressed as twice v1 plus 1 times v3. And you can check that if I take 2 of this vector plus 1 of that vector, the result is exactly that vector in the middle. And so this set of three vectors was not linearly independent because its homogeneous equation, because it had a free variable in it, the solution to that homogeneous equation was not unique, and therefore there exists a non-trivial linear combination of those three vectors, the columns of my matrix, which gave me the 0 vector.